Spirits are high. You can tell by the banter. It's the weather, isn't it? Maybe close to the end. Okay. Is there anything I should maybe cover before we jump gears into another topic? I think this topic will be extremely useful to a lot of you down the road. I wish I had time to give you a homework problem on it and make everybody do it, but I'll offer 10% extra credit, midterm credit if you'd like. So if you're needing more points, you could code this up, do the Gibbs sampler for it, and turn in a one-page report on it. So not anything too grueling, but it would be associated with that homework problem where we sampled from 4 different normals and collected data. We'll talk about that example, and that's how I'll frame the example to tell you generally what's going on. I'll tell you kind of like what the deficiencies of Bayes are in that example if you just do the parametric thing, and I'll show you how to correct it next week as well. So there's been a lot of developments in the last 20 years in Bayesian methodology given the power of computers and Gibbs sampling. Anything I should cover that you guys don't understand? I thought Jenny asked a really good question at the end of last time. How do you put a variable back in through SSVS? And it's really just inverting that Bayes factor and then using that to compute the posterior probability of everything. So it's really just tracking those X matrices, which columns are in there, and updating that posterior probability and doing the coin flip and deciding if you want to put that variable back in. There are other strategies. We kind of came up with a proposal where we're just going to knock something out or push something back in one at a time. You could be more ambitious and change the whole vector, but you probably will, probably a lot of those things will have fairly low probability, And so updating everything all at once is, maybe not the best strategy ever. And so you get very low probabilities if you try to move your models really far away from somewhere that's already pretty good. And so there's a lot of ideas in there. You're building an algo of how to update everything. So hopefully it makes sense. Does it make sense now? Yes. So it's really just tracking that X matrix. And if you kind of know the -J sort of indexing in MATLAB, it's really easy and you don't even have to do a memory swap to do everything. Okay, so in Spirit, it's easy. You just have to always run a forward simulator, know what you're looking at, work with some easy examples to debug your code. And so I always have a simulation study right next to everything before I apply anything to real data, because then I know if everything's working. So I always feel like with the computer and with a proper simulation study, I can self-diagnose my code. How do I do it? It's always this frequentist thing, right? I run things over and over and over again, and I see if they're right on average. And so I apply these asymptotic frequentist ideas to debug my Bayesian code. That's always true. So, kind of cool. I kind of like that. That's called a compromise, right? Something like that. Okay. Shall I begin with something new? Mixture models. Okay, so what I'm talking about here is additive mixture models. So we've seen scale mixture models. If I mix anything over a distribution, we call that a mixture model. And there's different ways to do it. In this case, I'm going to be mixing over an additive form of distribution. So not just a scale mixture model, but I'm going to be changing the locations and the distributions themselves. So this in general is a mixture model. So it's an additive mixture model. So it looks something like this. So I'm going to have some distribution, and I'm just going to call this maybe f of x. And maybe I'll suppress some notation and not tell you all of the parameters in all of that. Or maybe I could just tell you something like this. I can write it out. Xi's are going to be distributed according to something. Then I don't have to tell you what all the underlying parameters are. But this is going to be a sum. I'm going to index my sum using k. K is going to go from 1 to cap k. And so this is going to be your number of mixture components. And I'll address the problem that I gave you for homework so that you could understand the difference between a posterior probability and a p-value. But in that example, cap k was 4. And I'll write that out explicitly in a minute. But this is going to be some mixture weights, pi k, this is going to be the probability of being in the kth component. And then I'm going to have some model for that component. And so I'm going to write it out in general like this. I'm just going to call this f of x right here. So that's the random variable, and this is an instance of that random variable. And it's going to have some underlying parameters attached to it. And I can let those parameters change for the kth component. In general, I can let this parametric model right here change too. They don't all have to be in the same model class. So I can let this be k as well. So this is the model of the kth component. So in general, this is called a finite mixture model because there's a finite number of components. So finite mixture model. And this is the finite number of components. And it would be proper for you guys to say, what if I didn't know the number of mixture components? And we'll talk about that next. So in the kind of the problem that you were working with, you were assuming you knew how many components there were, and you had hypothesized values for each one of those components. The model that we used before, and I would say this is I goes from 1 to n, right here. The model that we used previously were normals right here. And we had mixture weights attached to these. So there were 400 samples, there were 300 samples, there were 200 samples. No, it went 400 samples, 200 samples, 300 samples, and 100 samples from components that use different means. I'll write that down in a second. I looked it up this morning and saw what you guys did for your homework. In general, the sample from this model, here's what you do. So I'll just, since these are probabilities, these have to be numbers that live between 0 and 1, and they have to add up to 1. So I'll just write that out. That the sum of the pi k's is equal to 1. So these are probabilities, and the pi k's live between 0 and 1. You probably wouldn't let them be 0 or 1 because then the notation would be pretty superfluous, you know, that there wasn't a component there. So usually we would let this, for it to make sense, is they wouldn't be strictly 0 and 1. Okay, so this is how you sample from these. So sampling, this is in the forward direction. So how I sampled the data. Later on, we'll build a Gibbs sampler for inferring what the parameters are, and that's what I call the backwards sort of thing. So in statistics, we start with probability models, and it's really just math class. There's no inference. And then for backwards inferring, doing the inverse thing, then we do inference, and then it becomes statistics class. Very different. So sampling. So there's 2 steps to this. And so what I'm going to first do is I'm going to flip a coin. And I'm going to flip a coin with these probabilities attached to it so I can figure out which component I'm in. So really, if you think about this as a conditional probability, this is the probability of k component right here. And this is the distribution that's dependent on which value we sample right there. So I'm just going to write this out like this. Vi, and this is going to come from a multinomial distribution. So multinomials are just k-sided coin flips. So a multinomial with 2 sides, k is equal to 2, is a binomial. So very similar sort of concept. Multinomials. And this is going to have these different probabilities in here. pi 2 to pi k, cap k. So this is just a k-sided coin. Now I'm going to change my notation just a little bit. So I'm going to rewrite this so that you can see all of these random variables that we just introduced. I have a z right here. This is the component label. And this is going to be a value from 1 to cap k. And it's going to tell us which component we have right there. And it's good to think about this thing right here. Normally what you're going to get is you're going to get all these x's, but you don't actually get to see this label in general. We don't know which component the data came from. If somebody told you which component the data came from, life is really easy. You just do all the stuff I've already taught you to do. You plug in the data from that component and you infer its parameters. But in general, we have a mixture of data and we don't know where everything came from. So I'm just going to change my notation right here to this. This is going to be the probability that Zi is equal to k, right here. This is my pi k. And then I'm going to change the notation that looks like this. This is going to be f of x right here. So I'm going to be sampling these same xi's. And I'm going to have parameters associated with it. And while I know because of this indexing that I'm in the k component, I'll be a little bit redundant. And we'll use this notation and it'll help us to see Bayes' theorem. So this is going to be Zi is equal to k. And so now you can kind of see this hierarchical representation. This is supposed to represent exactly the same thing, but I'm building in some notation to tell you about this label right here, that usually we don't get to see this. So in general, we don't get to observe that, but it's part of the process for generating the data. And so then I'm going to take xi, and I'm going to sample it from f of x, given theta k, and I'll leave in this redundant notation. Zi is equal to k. So if Zi is equal to k, then I sample xi out of the k model. So this is this hierarchical approach. I kind of like writing it out this way because I can see this joint probability right here. What you really get from this sampling is you get a Zi and an xi at each step. And what we get to see as statisticians typically, or data scientists, engineers, whatever we are, is we get to see the x, and we don't get to see that. If you know about the EM algorithm, you've studied this problem, that's your latent parameter, and that's the thing the expectation step is over before you move to maximization. I'm going to be showing you a different approach for studying this problem where you get joint uncertainty over everything, i.e. you are going to be sampling from the posterior distribution. So there's maximization procedures for solving this fast, but if you wanted to know all your joint uncertainties, then you do the Bayesian thing. Okay, and you just repeat this over and over and over again. And so at the end of the day, you wind up with something that looks kind of funny, you know, depending on what these f's look like. So let me give you an example. This is the example we studied in homework. This is a Gaussian mixture model. And again, this is going to be a k-component finite mixture model. Later on, I'll tell you how to deal with this if you didn't know it. But ultimately, you put a prior on it. So if you didn't know something as a Bayesian and you wanted to learn it, you put a prior on there. Kind of the obvious choice for prior, since this is a count, is maybe a Poisson. And the trouble with that is that you have this very parametric form of something. So if I pick lambda in my Poisson to be relatively small, I'm going to heavily influence how many components are there. So there's these new approaches that have showed up I would say about 15 years ago, they became wildly popular, although they were surmised in the 70s. But there's these semi-parametric approaches that have more flexibility and don't constrain things with your parametric assumptions so much. And I'll tell you how that works. I'll try to make a connection between your homework assignment, what the p-value guy is trying to do, and what the Bayesian is trying to do. I think the Dirichlet process thing is kind of a nice compromise. I'll tell you about that next week. So here's my Gaussian mixture model. And this is a 4-component mixture model. I goes from 1 to 4. I'm going to have these different weights. I'll just write them in using the old notation. And then I'm going to have normals. And I'll be clear about where the x is. You're going to have mu k, and you're going to have sigma k. I think for our problem, what we did is we let sigma be the same for everything. Now, that's fine, but we could let it be different if we thought that each component had different variances. I think for right now, I'll plug it in as k right here, but if you would like for your extra credit offering to leave that as just something that's common across all models, that's totally fine with me. So keep in mind, you'll have to infer things through this form right here. Your likelihood would come out of this big form. So.
I think my question is, let's say that the xi coming from x.
Yes.
Do you mean that some xi's come from 7k and some come from 1?
Yes, that's right.
Or the summation?
But there's no sum. We're not adding them together. What we're doing is we're doing these two steps. So if you want to think about this formula as a process, you first flip the multinomial. So i.e. you sample from this thing, then you plug into the conditional, and you sample the x. So that's what it means, and that's why I like to write it out like that, because you can see that process built into that thing. So when I see integrals and stuff like that, I see processes. So how would I do this on a computer? That's the way I always think about it. That might help me. So yeah, we're not going to add anything together. So this will probably make some sense to you after we kind of study it in the context of this model right here. I'm going to let, we'll come back and we'll talk about sigma k later on, but I'm going to say this is known. And if you want to do this for your homework, the extra credit offering, and let it be known and plug that thing in, I think it was 5 or something like that you'd done on the homework, you can plug that in. If you didn't know it, how would you learn it? You do Bayesian updating. So you'd probably use something like a gamma prior, or at least the limit of the gamma prior, 1 over sigma, 1 over sigma squared, 1 over phi, depending on how I parameterized everything. And then I would have a separate updating step for that. You just iterate. It's the beauty of Bayes. There's another thing you don't know, you just plug that thing in. So it's all very modular. You have a Gibbs step for it. Okay, so I'm going to say pi k. This is going to be equal to one of these things. So 0.4, 0.2, 0.3, 0.1. So this is the same as 400 over 1,000. Just to be clear where those numbers are coming from, these are the numbers that you used on your homework. And so mu k's are going to be these elements right here. So, and they're going to correspond to these weights. So this is going to be a 10, a 15, a 17, and a 20. I just want to point out that if I ended up looking at this sum right here, k goes from 1 to 4, and I tried to see what the average of this process was, the average would be these pi k's times the mu k's. And that has some number attached to it. So I just multiplied this times this times that, this times this times that. And this number is approximately, does anybody know what it is? I think it's like 14.2, if my memory serves me. So something like that. 14.2 is what this is. So I just want to address this, what you learned in the homework. You didn't sample these randomly. You just fixed these at these values right here. And you sampled 1,000 times from that. So on average, the analysis you did is going to be like the analysis I'm going to teach you here, but instead we're going to learn all our joint uncertainty about the parameters. Instead of trying to do hypothesis testing, what you really should do is do estimation and try to learn all the parameters of that model and not hypothesize anything. So that's the thing I always try to talk people into is don't do hypothesis testing, do estimation. So then we can agree with each other. We don't have to have this question of how close to the hypothesized value do you need to be before you're willing to reject it. And that's how all schemes differ. So just questioning the closeness clause. Bayesians are always relative, and in some sense, the p-value person is using absolute distances. Okay. So the Bayesian answer, when you ended up sampling 1,000 of these, and I'd say if I followed this schema right here, well, my data wouldn't look exactly like yours. I would approximately have 0.4, 0.2, 0.3, and 0.1 coming from each component. So in essence, I could generate data that's very similar to the stuff you generated. I'm going to teach you how to do this problem correctly now. But when you did hypothesis testing, and you were hypothesis testing the mean, and you knew what this is, and they all have the same variances, 14.2 is closest to that. Now, if I did let these variances distance differ, I would have to talk about the relative distance with respect to its variance. So what's the standardized score of it, and which one is smallest? And that would be the one it's closest to. Since the variances are all the same, I can just look at the distance from this number to all of these. They're all being compared on the same scale if that's the same. So 14.2 is closest to 15 out of that. So the Bayesian answer when we did this hypothesis testing thing, which is incorrect, you shouldn't do that because you're using the wrong model. But my argument is we're always using the wrong model. And so we might be able to come up with better comparisons than I asked you to do in the homework, but that was supposed to illustrate something, the big differences between being a Bayesian. The Bayesian's closest to this, and it's being compared to those. So as you get more and more sample, it ends up saying, well, if those are my choices, and you're going to force me to pick one of these, then I'm going to pick 15. And so that posterior probability was climbing to 1, and all the other posterior probabilities were climbing, converging towards 0. And they all added up to 1 because everything is relative. I kind of like that. Although the way the comparison was set up, it's just kind of nonsensical. So if I walked in, I said, now this is the truth, I would be wrong. It's the best choice compared to all of these. Unfortunately, the model that we're sampling from looks like this, and it doesn't look like a one-component normal. So we made a fatal flaw. The p-valuists, I kind of think they're the winner in this conversation, although in general, I don't think this is what you want, because I think it's always true. The p-valuist says all of them are wrong. All the p-values are decaying towards 0. And if your null is wrong, that's what a p-value will do. And what you notice is that the p-value associated in the two-sided test with 15, that one converged the slowest towards 0. So it's really that rate of decay. If the null hypothesis is true, the p-value is uniformly distributed. And if the null hypothesis is not true, then a p-value will decay towards 0. I might ask you on the final to work out like what a p-value looks like under an alternative hypothesis. Something like that. Maybe. I haven't decided exactly my questions. I'm close. So, and that's as good as I ever get. Okay, so the p-value person says none of these models look good. This is the trouble with p-values in general when you're doing the sharp test. There's usually something wrong. It's not just the mean in this case, it's the model itself. And all of them don't explain the data very well. The Bayesian is going to say it's compared to whatever you've set up. And so if somebody says like, well, the posterior probability of this model is whatever, 1, I don't think it's good enough to say, well, that's pretty good. It's what did you compare it to is the real question. How did you set up your comparison? I don't care that the posterior probability is 1 because it's relative, it's all conditional. And so it's all about the comparison. The p-valuist doesn't really do a comparison. The alternative hypothesis just tells you about tail direction. And since we're starting with the sharp test, there's no recourse but to just do that typical thing. It doesn't have a built-in thing to compare. I will point out that p-value ratios, if I compared all the p-value ratios, asymptotically they would behave like the base factor. And so, which is, in some sense, has some commonality with the posterior probability. There's a one-to-one transformation between that base factor. So I usually tell people, come up with alternatives if you really want to use a p-value, and then set up your p-value ratios. And I'm trying to get them to be a little bit closer to being amazing and do something relative. Okay, what I should say about this, so this is going to come up next week. The Bayesian does have a method for applying a prior decay, and it'll do a compromise between these two ideas. It'll compare everything to everything that's in the model that you're hypothesizing against, what your alternatives are, but it leaves another little possibility that it says it's possible that it doesn't look like any one of these hypotheses. And so I'm going to generate a new distribution and say maybe it's like that one. And I kind of like that. And I think that is what you want to do. If it doesn't look like anything here that you've pre-specified, maybe it looks like something different. We don't want to throw all that data into the wrong components. So a Dirichlet process does have the ability to say it doesn't look like anything that we've seen before, open up something new, a new component. I kind of like that. So that falls into the class of Bayesian semi-parallels. I'll tell you a little bit about it next week. Let's stick with this case that we know what K is. We won't treat that as random yet. Okay, so just a little dialogue between what's the difference between a Bayesian and p-value as Neyman-Pearsonian if we were doing hypothesis testing. Let's forget about all that. Let's do the right thing and actually just try to estimate this. So usually when I see data and it's lumpy, I think, oh, it's coming from some mixture model. And I build some mixture model and I check to see how well it fits. I look at diagnostics, I look at residuals. What I really look at is I always pull a holdout sample out and I build my posterior predictive distributions and I see if they overlap my holdout sample. So what am I doing? I'm doing something frequentist. So it's not a big deal. It's okay. So I'll do something kind of frequentist to validate my model. And if I don't like it, I'll rebutter it up, come up with another model and see if I can do better. I see where the residuals are missing or the posterior predictive distribution isn't covering, and so then I modify my model. So that's my Bayesian, non-Bayesian compromise. Okay, how does a Bayesian handle this? There's lots of things that they don't know. You don't know the mu's. Possibly you don't know the sigmas, but we'll just leave that out of the conversation right now. But you also don't know the z's. And the z's are part of the process, and you need to infer it. For a Bayesian, if you don't know something, you place a prior on it, and you learn it. And maybe you average that out, or something like that if you didn't want to look at it. And if you're doing Gibbs sampling, by averaging it out, it just means that you just don't print it out to yourself. And that's the marginalization. Okay, so we don't know. Mu k's or the z's. So we need to learn them. But just real quickly, let's say I did know the mu's. Let's say I knew the mu's and the sigmas. So just as an example so we can see what's going on, say we knew mu's and sigmas. So let's say I had something like this. I've got 0.4, 0.2, 0.3, and then 0.1. Sorry, these should all have the same sort of width because they have the same variances. I'll just plug in what these are. So this is 10, this is 15, this is 17, and this is 20. I know that they probably overlap a lot more than that, the actual data that you generate, but this will at least convey a point. So if I saw a data point right here, xi, could you tell me which component you think it came from? Which one? Yeah, this one. It's pretty obvious. Why? Because that's closer to that than it is to any of these relative to their variances. So this strongly falls into the tail of that distribution. And so I could come up with an associated probability that this lives in that component. And so if I saw a point right here, could I tell you which component it came from? I could still guess. This would probably have about 0.5 probability of coming from that or from that. It would be relatively close. And so this is what Bayesians will call, and computer scientists and engineers will call sometimes soft thresholding, i.e. we're using a probabilistic rule. So we're not just saying that's what I think it is with absolute certainty. Instead, you're assigning a probability to it. I want to point out that this is very similar to clustering. So this is what I would call Bayesian clustering, where I know how many clusters I have, and I'm willing to parameterize what those clusters look like. So those of you that know about the k-means algorithm, k-means as an algorithm is a deterministic method. It's not probabilistic. If you don't know what it is, go look it up. It's a relatively simple iterative scheme. But it's assuming normality, and it's assuming that all the variances are the same, and they're circular in high dimension. So i.e. it's sigma squared times the identity in high D. And so a Bayesian could fit a mixture model to that and come up with a soft thresholding rule where you have probabilities expressing your uncertainty of where everything comes from. Okay, so if you knew what the mu's were, you could learn what the z's were for each xi. And if I knew what the model parameters are, if I wanted to learn whether or not that lives in one of these 4 components, I wouldn't need any of the other data to do it because I know what the model parameters are. The other data doesn't help me. So, however, we don't know what the mu's are. So we're going to be using all of the data to try to infer the mu's through a Gibbs sampling step. And then we're going to run through all the z's and see where they go. And then we're going to iterate back and forth. We're going to learn the mu's, and we're going to learn the z's. We're just going to iterate these 2 steps. I've already taught you how to infer mu's. Let me just remind you. And then we'll just combine these 2 ideas, and then we'll have a mixture sampling. So if we knew the zi's, we could learn the mu's. So what I would do to learn maybe mu1, so mu1, I would say is distributed according to some sort of a normal distribution. I'm going to use x bar right here, but this x bar, so normally we use x bar and then we'll use sigma squared and we'll divide it by n right here. This is typically what we do. So this was the Bayesian procedure. My assumption in this is that we used pi mu is proportional to a flat prior. So this posterior distribution depends on some prior. But if I knew what the z's were, I don't want to plug in all of my x's into that. I only want to use the x's that came from the zi's are equal to 1. So that's going to be my notation for that. So this is going to be the sum of the xi's right here. And I'm just going to write this down maybe a little bit. Well, I'll use a different index just so I don't confuse you. So xj's, where the j's are going to be an element of the x's, or this is going to be the element. So I'll write it out like this. So This is going to be the numbers let me write it out like this. This is going to be, J is going to be, I'll do it like this. Xj is an element of the xi's such that zi is equal to 1 right here. So what this says is these are going to be the x's that are associated with zi equal to 1. So set notation is, these are the collections that I'm going to be having, and here are the conditions that need to hold for me to design that set. If you're not used to set theory notation, you just think of it this way and write it out in English. So these are all the xi's that have a corresponding pair of zi's equal to 1. So we're going to assume we know what the zi's are. And this is going to be the number of those. And I'll write it out like that. Number for 1. This is going to be the number of xi's such that zi is equal to 1. So in your case, they would be the first 400 numbers you generated. And the n would be 400 in that case. Of course, if I randomly sampled it, it'd be surprising if you came up with exactly 400. It would be something close. So if n was equal to 1,000. And so I would condition on the x, I'll write it out using the same thing, the xi's given that zi is equal to 1. So those are the data points that I'm going to condition on. So, and then I'm going to divide this, of course, by n1 as well. And I'm going to change that to n1. So if I knew what the z's were, I would just take the x's associated with those components. So I would just partition all of my x's into the ones where z was equal to 1, z was equal to 2, z was equal to 3, z is equal to 4. I'd grab all those x's and I'd compute these posteriors. And life would be easy. You'd do exactly what you already know how to do. Now we're going to combine these two ideas. We're just going to iterate back and forth. So of course I have to teach you how to compute that probability. We'll see if we can figure it out. So here's your Gibbs sampling. So this is going to be 4. You're going to run this a long time. I need to initialize something. So I could initialize all the z's, or I could initialize all the mu's. So maybe I'll initialize all the mu's and then start updating z's first. You have your choice. I couldn't tell you which one is better. Again, this is an iterative scheme, so if one is better than the other, it's only by the way you initialized. So, you know, maybe initialize the mu k's at t is equal to 0. And I'll do this for k goes from 1 to 4. Of course, if you had a higher number of components than 4, you'd have to plug that in. So I've initialized those. So step 1 is I'm going to update my z's. Using, and I'm going to have this little for loop built in here. For I goes from 1 to n. So I'm going to have to run all of these. If you're worried about speed, you can do these all in parallel. They're all independent of each other. It's a trivial thing to parallelize. So I'm going to take my zi's and I'm going to sample these from it's going to be a multinomial distribution. So I'm going to say from my probability distribution on the zi's, given everything else from this full conditional. I'll tell you what this probability is in a moment. Just plugging it in as a placeholder. And then we're going to update our mu's. So then I'm going to run through 4, k goes from 1 to 4. And this is going to look like mu k is going to come from its posterior distribution. This is going to be for the t index, and I should index that with t as well. And I'll say given everything else. Bunch of parameters in there. So we like this full conditional notation because I don't have to enumerate everything. So that's a Gibbs sampling. Okay, we know how to do these right here. We're going to use that step. Of course, after I reassign the z's at every single step, these x matrices, these x's right here are going to change. So they're changing at every step because I'm re-updating the z's, their association with one of the components. So basically, I'm just going to be flipping a bunch of coins in here. And then once I have those z's, I'll recompartmentalize my x's, and then I'll resample my mu's from this. So this is going to be mu1. So I think we know this step. All we need is that step. The question is how do you do this? Probability that zi, I'm going to say, let's just make this zi is equal to 1. Okay, so that we have the first component. We're going to have to do this for all 4 components. Really, you just need to do it for 3 of the components because we know the rule of probability that everything adds up to 1. So you just need to do 3, add those things up, and take the difference from 1, and that'll be your 4th one. So this is given everything else. Now keep in mind, we would want to know what all the mu's are. In the sigma, of course. And we can figure this out. And I just want to rewrite our original mixture model. It looks like this. Probability of zi is equal to k times our normal. I'm going to write it out. We'll keep it as a normal. But you could change all these distributions to anything you want, and you're not constrained to having them of the same parametric family. But this is going to be x given mu k and zi is equal to k. So I want to just point to this. You know what that is. And what you would like to do is flip this around and put it on the other side. So let me just ask you a question. Given the mu's and the sigmas if you'd like, how many of those xi's are going to help me to tell me what the probability that zi is equal to 1? And it's just like that picture I drew you. For you to answer this question right here of which component do you think that's in, Warren said 1. A lot of you did. It's in the first component. You didn't need to know where all the other data was to answer that question because you know what the mu's are. That confuses you. Where does all the other data come into play? It comes into play in learning the mu's. So it gets compartmentalized there. And then all of a sudden, given the mu's, learning which zi component everything comes from, you only need 1 data point. So you really only need xi. You don't need any of the other data. It's independent because we know what the parameters are. And this is going to be the mu k's. I'll write it out like this. K goes from 1 to cap k. That's a 4 right here. I don't like to write out mu1 through mu4. That's what that says. And then we've got our sigma k's as well. We're going to assume this is known. So we're just going to plug it in. Again, if you didn't know it, you do the same sort of thing that you would do right here. Or given all of those x's associated with a component, you would sample from its posterior distribution, which is going to be a gamma distribution if you used the conjugate prior. So how do you get this? And this is why I set you up to look at this notation right here. And I like it because now you can see Bayes' theorem. You just apply Bayes' theorem to this, right? So it's going to look like this. Ni xi given zi is equal to 1 and mu1 right here. Then I'm going to have my prior. So this is going to be my prior. We've got a lot of these weights running around. I don't want to write down pi k because that might be something different. We'll have to discuss this in a moment, how we pick that prior. But if you knew something and you knew that I happen to oversample component 1, you'd probably use that information. So what does this look like right here? This is going to look like the sum over everything else. So k is going to go from 1 to 4. Normal xi given zi is equal to k, where that's the index, and associated mu k right here. Again, we're going to assume we know sigma, so I'm not going to plug it in. This is Bayes' theorem. Oh, and then I'm going to need my little priors on k. So that's Bayes' theorem. That's it. So if you use the right notation, you'll see what to do almost instantly. So your Gibbs sampler is just going to come up with these probabilities, compute them. If you want to compute all 4 of them, then what you're going to do is you're going to flip that 4-sided coin right here. So I'm going to compute all the probabilities, and then I'm going to flip a 4-sided multinomial with these 4 things right here that I would compute. And I would do this for all 4 components. I'd flip that coin, and then I would come up with a number right here. It's 1, 2, 3, or 4. Then I'm going to plug that in right here, and I'm going to sample. Then I'm going to get however many x's are associated with that component, and then I'll sample my u out of that. Jenny?
So this assumes we know
This assumes you know k. Yeah, that's right. So that's what I said. Yeah, so I will teach you about not knowing k. I've never done that in a Bayes class yet, but I think maybe that's the new thing I'll throw at it. Yeah. What if you didn't know k? We'll talk about that next week. Sometimes you know k. So like if you're working with cellular data, there's like 16 channels or something like that. And so you're going to associate things with one of 16 channels. Why do they know that? Because they know, And they basically do this. So they don't know which channel things are coming from, and so they'll do this Bayesian thing. A lot of times they don't call this Bayes. So they'll do this step and they'll just say this is something different. So I've heard people call this the reliability index so that they can avoid Bayesian language. So Chris Bishop, that's a well-renowned Bayesian, does call that the reliability index for engineers that get a little bit spazzed out because they heard the word Bayesian and the word prior. Question is how do you pick this? If you didn't know anything, you might pick it to be 1 over k. And assign equal mass to everything. So there is a reinforcement learning technique that I could look at every step of the algorithm and see how many of these zi's were corresponding to that component. And I could change my prior. Keep in mind, that's not a real Bayesian technique when you're chasing your prior. So you'll converge to the right modes, but your uncertainty won't be expressed right, because you're fluttering that thing around. And so it's unclear what that is. If you knew these pi k's, you could plug these in. So in the EM algorithm, you kind of re-express that and you use your previous step to update those indices. So you'd converge to the right maximum and you'd probably do it faster, but you would under-express your uncertainty about things. So I don't like to do that because that's what I think the most important thing is the uncertainty. And so probably in most cases I would pick that, but if you told me up front what the pi k's were, that 0.4, 0.2, 0.3, and 0.1, and you knew that, I would choose that. So, but if you didn't know that, I would choose the flat prior. So, and I think that's all you do. So let me just make a note, extra credit. 10% midterm. Jenny, I looked it up, it was 30%. Actually, let's say 10% final, because that one's 40%. Final. So if you need points, they're easy to get. Extra credit. Code this up for the homework mixture problem. That was in homework 4. And turn in 1-page report. If you need 2 pages, that's fine. So show me some graphics, tell me what the problem is, write the basic formula in there, and show me that the thing converged. Show me a trace plot or 2, something like that.
Except that we can say sigma squared is known now, right?
Yeah, absolutely. So really, I just want you to get the basic idea. Those of you that do signal processing will see this problem again. So this is the most typical way to do everything. So you might have the EM formula, but if you want to do the full Bayes thing and express uncertainty and come up with real predictions, then you'd probably do this.
So we're also assuming that units will not be.
Yeah, so let's come back, ask me that question next time. I will tell you this, that for any smooth distribution, that I can express it as a mixture model of normals. So it's just kind of a smooth function that you can use. And so to kind of build everything up. A lot of times you don't know things are normal, so you might change those distributions. So, but if I don't know what the distribution is and it's something crazy, then I might model my distribution as a mixture of normals because I know I can capture any trend, and it's just a question of how many normals do I need to end up expressing whatever that distribution is. So this is one of my favorite tricks. What I always do is I always put a Cauchy component at the very end too, so that if there are these outliers out there, my Cauchy component can catch them, and it doesn't contaminate that data with another mixture component. So if I'm not going to do the Dirichlet process thing, then I usually add a Cauchy at the end that can grab things that just look different. So otherwise I do the full-blown Dirichlet process thing that I'll tell you about next week. So I think simple idea, and this is basically Bayes in a nutshell. Figure out your full conditionals, make a Gibbs sampler. At least that's probably 10 years ago, that was the only thing going. Now people do variational Bayes and all kinds of other stuff. Okay, have a great weekend, you guys. We'll do a review next Wednesday, and I'll tell you more about stuff that I won't test you on. I'm going to deliver the final on the 12th to you. That's Sunday. And then I'm going to ask for it back by 5 p.m. on Wednesday. So it'll give you 3.5 days to work on it. Totally. Yeah, exactly. It's going to be 10 problems or so that I'm going to give you. And they're going to basically, if you didn't learn the material through the class, this will be your last chance to, oh no, I get it. So I'm going to try to design the questions that it's not just hard, but it helps reinforce what you learned. Hopefully everybody gets an A. That's what I'm doing. Jenny, let me shut off. Yeah.